Hello guys, my name is IBM and I am solving 9702 that is component 22 May June 2024. This is AS level structured questions. My email is sevia22@gmail.com. So without wasting time, I would like to take you the question paper. So this is the question paper which I think my students must have done this one, and I think about 3 students might have got everything correct in this paper. 2 or 3 students, I expect them to score almost 60 or to lose at most 2 marks, because I think component 2 was the easiest component for this May June series. So I'll not go through the instructions. I'll not go through the constants, the data given, the formula. I'll go straight to question number 1. So the list below shows some SI-based quantities. SI-based quantities. This is the first unit in AS physics, physical quantities and units. And I think there are 7 base quantities. These include mass, length, time, temperature, and we have what we call amount of substance. We have amount of substance, we have luminous intensity. This is 1, 2, 3, 4, 5, 6. And of course, we have what we call current. These are the 7 physical quantities: mass, length, time, temperature. To be specific, for temperature, it is absolute temperature or thermodynamic temperature. Then we have amount of substance, luminous intensity, and then current. So the question is underline the quantity that is not an SI-based quantity. So charge is not an SI-based quantity because we have mentioned the current, we mentioned length, we mentioned time. So the answer is going to be charge. A square solar panel with sides of length 1,300 millimeters is shown in the figure. So it is a square. You should remember that is a square, so all sides are equal. Light is incident normally on the solar panel. The power of the light incident on the solar panel is 750 watts. Calculate the intensity of the light. So by definition, we know that intensity is equal to the power over area, or power per unit cross-sectional area. So I'll just substitute. The power is given as 750 watts divided by the area. So the area is going to be, of course, I have to change. The area is going to be 1,300. I change it to meters, so it will be times 10 to the power of -3, but this should be squared because it's length times side times side. So this will be 1,300 times 10 to the power of -3 to change it to meters, and this should be squared. So I'll just check with my calculator. 750 divided by 1,300 exponent -3, and this is squared. So that is 444. I will write 444. I can write 444 watts, or you can write 440. So to 2 significant figures is approximately 440 watts per meter squared. Or you can write 444. That is 444. Yeah. Then the percentage uncertainty in the incident power is plus or minus 3%. The uncertainty in the length of each side is plus or minus 5 millimeters. Remember, the area is equal to the one side times another side, which is L squared or side squared. Calculate the percentage uncertainty in the intensity of the light. So remember, intensity is power over area. Intensity is equal to power over the area, which is side squared. So if I want the uncertainty in each of these, so it means the percentage uncertainty in intensity is going to be the percentage uncertainty in the power plus twice the percentage uncertainty in L. Because L is squared, so it will be twice the percentage uncertainty in the length of one side. So the percentage uncertainty, I can find the percentage uncertainty in L first, but of course I know percentage uncertainty in L, or let me say the absolute uncertainty in L or the percentage uncertainty in L alone is going to be 5 divided by the value of L, one side. One side is 1,300, so this will be over 1,300. I don't need to convert the units because this is millimeters. This is also millimeters. Then I'll multiply this by 100 to make it percentage. So I'll say percentage in I equals to percentage in P, which is 3%, plus 2 times percentage in L, which is 5 over 1,300 times 100%. So this will be 3% plus, let me press the calculator here, 5 divided by 1,300, then times 100, then I'll multiply this by 2. So this is giving me 0.77 to two significant figures, 0.77%. So when I sum up this, it is approximately 3.77%, or you can write 3.8. I'll write 3.77. So it is 3.77%. Then the useful power output of the solar panel is 160 watts. Calculate the percentage efficiency of the solar panel. So this is the useful power output, then the percentage efficiency. We know that by definition, efficiency is equal to the useful output power divided by the total input power. Because it's required to be in percentage, so I'll say times 100 to make it a percentage. So this efficiency is going to be, the output is 160 watts. Then the input, I think it was 750. So this is 750 watts. Then I multiply this by 100 to make it a percentage. So 160 divided by 750, then times 100. So that is 21.3 recurring, or approximately 21%. To two significant figures. Another square solar panel is placed so that light of the same intensity, so intensity is the same, is incident normal on it. The new panel has shorter sides, so length has decreased than the original panel. The new panel has the same power, so power is remaining constant. The same power output as the original panel. State and explain whether the efficiency of the new panel is greater than, less than, or the same as the efficiency of the original panel. So I will do this mathematically here. We know that efficiency, I'll use small letter e for efficiency, is going to be power output over the power input. This is the same as the power output. Remember, power output has remained the same over the power input. Also remember, intensity is power over area, which means that the power is equal to intensity times area. So this is going to be, power input is going to be intensity times the area. This is the same as power output over intensity, and the area is length squared, or side times side, which is side squared. So they have told us the power is the same. So I'll put a star on power output. The output power is the same. The intensity is also the same. I will put a star on intensity because it's the same. So they have told us this new panel has shorter sides. So that means L has decreased. So if L decreases, it means the area has decreased. Remember, the power is the same, intensity is the same. So if the area has decreased, it means the power output is the same, but the input intensity has decreased. Because efficiency is inversely proportional to the input intensity, it means the efficiency increases. Okay, so I will simply put this in writing and I will say shorter sides. Shorter sides means the area of the new panel is less. That's number one. Many times when you're answering such equations, please look at the marks and ensure that what you have written is able to or can give you those marks. So shorter sides means the area of the new panel is less. So the input power of the new panel is less than the input power of the original panel. So the input power of, remember the input power depends on the length or the area or the side squared. The input power of the new panel is less than the input power of the original panel. And if the input power of the new panel is less than the input power of the original panel, efficiency is inversely proportional to the input power. So I will simply say hence, efficiency of the new panel is greater than that for the original panel. Hence, efficiency of the new panel is greater than that for the original panel. Okay, so that would give you, I think that would give you the 3 marks. Question number 2. Skydiver jumps from an aircraft at time t equals to 0 and falls vertically downwards. The variation with the t of half velocity v is shown in the figure. So we see that this skydiver reaches terminal velocity as shown by the graph. Using figure 2.1 state the terminal velocity of the skydiver. So I'll just put a ruler here on the graph to see where this line touches the y-axis. I think this is the point. And the scale on the vertical is, I think it's 1. So 35, 36, 37, 38. This is 39. So the terminal velocity is 39 meters per second. Then by drawing a suitable line on the figure, determine the acceleration of the skydiver at time t equals to 9 seconds. So I have to rub off this because this is not the line required. So I have to clear off this. So at 9 we have to draw a tangent. So the scale on the x-axis is, I think, 0.5. So I think 9 is here. This is 9. So I must draw a tangent at 9. Okay, so I've tried to draw a tangent between this point here and this point here. So I'll just use a triangle between those 2 points. Let me change this to a pencil maybe. So I'll draw a tangent. I've drawn a tangent and I'm going to draw a triangle between these 2 points to use these 2 points to find the gradient, because the acceleration is the gradient at that point. Okay, so now I'm finding the acceleration. So I'll say acceleration equals to the gradient of the tangent line. So this is of course equivalent to change in v over change in t. So change in v, I think this is 26, and then I think this is going to be 44. So on the vertical axis, I have 44 minus 26. Then on the x-axis, I have, I think this is it this one? No, it's this one. I think this is this 18? So 15, 16, 17, 18. So that is 18. So 18 minus 0. So this will be 18 minus 0. So let me just press my calculator. 44 minus 26 divided by 18. So this is giving me 1. So this is going to be 1.0 meters per second squared. So the acceleration is 1.0, or exactly 1, because it is just exact. So that is the acceleration. Then the mass of the skydiver and her parachute her equipment is 68 kilograms. The upthrust on the skydiver is negligible. After reaching terminal velocity, the skydiver opens her parachute at time t1. A total drag force of 1,800 newtons acts on the skydiver. Determine the magnitude and direction of the acceleration of the skydiver at time t1. Okay, so because the skydiver opens her parachute at time t1 and the total drag force of 1,800 newtons acts on the skydiver, then I will just use a simple sketch here. Remember, the upthrust was negligible, so remember the forces which we expect to be acting on the skydiver when it's falling. We have the weight downwards, we have the upthrust, which is approximately 0 because it's negligible, and we also have the drag force, I'll call it FD, upwards. But at terminal velocity, of course, upthrust plus the drag force should be equal to the weight downwards. So since the upthrust is 0, and is falling downwards, so I would simply say the resultant force is simply going to be equal to, because after reaching terminal velocity, the skydiver opens her parachute at time t1. A total drag force, because he had already been moved, the resultant force was already 0. In other words, the weight was equal to the upward force. Now again, he opens the parachute. That means the drag force is going to be greater than the weight. So the resultant force is going to be the drag force, or I will say the drag, minus the weight. Because before opening the parachute, the weight was equal to the weight was equal to the upward force. Then when they open the parachute, it means now the drag force or the upward force is greater than the weight downwards. So the resultant force is going to be the drag force minus the weight. That's what we would expect. But then this could not be true, so I could have, because opening the parachute would mean that this person is going to slow down. That means the resultant force is actually in the opposite direction to that of motion. So the drag force is going to be 1800 minus the weight, which is actually m times g. So this is 1800 minus the mass. I think the mass was 68, then times g, which is 9.81. So this is going to give us an acceleration which is negative, I think, because it's actually going to be decelerating. So 1800 minus 68 times 9.81. So this is going to be negative 1132.92 newtons. The negative just shows that the resultant force is in the opposite direction to that of motion. Now I want the acceleration. Remember, the resultant force F is equal to ma. So the acceleration is going to be a negative 1132.92 divided by the mass, which mass is 68. So I'll just divide this by 68. So this is giving me negative 16.66. Or I can say approximately negative 17 meters per second squared. So the acceleration is going to be a negative 17 meters per second. What does the negative imply? The acceleration is in opposite direction to motion. So since the motion is downwards, then the acceleration must be upwards. So this is going to be upwards, which essentially means a deceleration. The parachute is fully opened at time t2. At time t3, the skydiver reaches a constant velocity of 5.7 meters per second. Describe and explain the variation with the time of the magnitude of her acceleration between t2 and t3. Okay, so it is fully opened and reaches a constant velocity, which means now it reaches a zero acceleration. So the acceleration must have decreased to zero. And why does it decrease to zero? It means the drag force must have increased so that the resultant force on the parachutist as the parachutist slows down, then the drag force also is going to slow down, is going to decrease, because remember, drag force depends, or air resistance depends on speed. Because there was a deceleration, it was slowing down. But as they slow down, it means the drag force also reduces because it depends on the speed. So I'll simply say the drag force or resistive force depends on the speed the drag force, or you call it resistive force, depends on speed. That's number one. But when the parachute is opened, of course, it's going to slow down. That means the drag force also reduces. So I would say as the skydiver slows down, as the skydiver slows down, the drag force also decreases. The drag force also decreases. What happens to the resultant force? Remember, the resultant force was drag force minus the weight. So the drag force is becoming smaller. So the difference here in magnitude also becomes smaller. So the resultant force decreases. The resultant force decreases in magnitude. The resultant force decreases, so the magnitude of the acceleration also decreases. So the magnitude of the acceleration decreases. Of course, when we reach a constant velocity, the acceleration has reached 0. So I'll say decreases to 0 at t3. Decreases to 0 at t3. Okay, then calculate the change in momentum of the Skydiver between t1. Remember at t1, I think t1 the speed was 39 meters per second. And t3 we have seen the speed is 5.7. So this is 5.7 meters per second. Remember at t1 was falling downwards, at t3 is still moving downwards. So it means they're in the same direction, but we want the change in momentum. So the change in momentum is going to be the mass times the change in velocity. So this is going to be the mass, which was 68. The velocity, let's say final velocity is 5.7. Initial velocity is 39. So that is the change in velocity. So this is going to give us a 68 into brackets 5.7 minus 39, which gives us a negative 2264.4, or approximately negative 2300 Newton seconds. So of course the negative just implies opposite direction. So here I can write, you can put the negative if you want, but the magnitude is the same. So negative 2300. Then question number 3, lightning occurs when charge builds up in the atmosphere, creating a PD between the ground and the atmosphere. During a lightning strike, there is an average current of 3.3 times 10 to the power of 4 amperes for a time of 2.6 times 10 to the power of minus 5 seconds. Calculate the charge transferred during the lightning strike. Of course, we know that charge equals to IT. So we just substitute. I is 3.3 times 10 to the power of 4. The time is given as 2.6 times 10 to the power of minus 5. So I'll just press my calculator. 3.3 exponent 4 times 2.6 exponent minus 5. So this is giving me 0.858. 0.858. Okay, so I'll record the charge as 0.858. Or you can write 0.86 coulombs. The PD between the ground and the atmosphere is 3.0 times 10 to the power of 7 volts. Calculate the average power in gigawatts transferred during the lightning strike. So we know that electric power is I times V, because they have given us V, and we know the current, I think. So I'll just use that directly. So this is going to be, the current is 3.3 times 10 to the power of 4. Then times V, which is 3.0 times 10 to the power of 7. So this will give me 3.3 exponent 4 times 3 exponent 7. So this is 9.9 times 10 to the power of 11. This is in watts. So we want to bring in a prefix, and your teacher must have told that to bring a prefix, you divide by its value. So I'll divide by the value of giga. 9.9 times 10 to the power of 11 divided by giga, which giga is, I think giga is 10 to the power of 9. So the answer here is now going to be in gigawatts. So I'll just divide this by 1 exponent 9, which is 990. So the answer here is going to be 990 gigawatts. Lightning rod. Lightning rod is attached to a tall building to conduct charge safely to the ground. Lightning rod is modeled as a uniform cylindrical copper cable of total length 95 5 meters and runs from the ground to the top of the building as shown. The resistance of the lightning rod is 9.6 ohms, that is resistance. Then the resistivity, so this is R, this is rho. Resistivity of copper is 1.7 times 10 to the power of minus 8 ohm meters. Determine the radius of the lightning rod. So we want to determine the radius. Remember from your electricity concepts, you know that resistance of a conductor can be given by rho L over cross-sectional area. And they have given us, do we have radius? Oh, they want us to find the radius. So area is equal to pi r squared. So this is going to be equal to, and area is equal to pi r squared. So resistance is going to be rho L over pi r squared. I'm just going to make r the subject. So r squared is going to be equal to rho L over pi times capital R under square root both sides. So I'll just say small r is equal to the square root of, I will just substitute. Rho is 1.7 times 10 to the power of minus 8. Then L, I think L was 95. The length was 95. Divide by pi. Then times capital R, which is 9.6. So checking my calculator, I have 95 times 1.7 exponent minus 8. Divide by, we have shift pi times 9.6, then under the square root. So this is giving me 2.31 times 10 to the power of minus 4. So I'll write here 2.31 times 10 to the power of minus 4. The radius of the copper lightning rod is doubled. R is doubled with no change to the length. L is not changed. State the effect of this change on the resistance of the lightning rod. Okay, so I'll first manipulate this here. If resistance is equal to rho L over pi r squared, which is the area, this is the original resistance. The new resistance, I'll call it R new, is going to be resistive. It is still copper, so that is rho. The same length, because they said there is no change to length, over pi, but the radius is doubled. So where there is r, I'll put twice r. So I'll put 2 small r squared. This becomes rho L divided by pi. There is a 4 here, so it will be 4 r squared, which is the same as 1 over 4 times the original resistance here. So it is a quarter of, so in other words, the resistance decreases by a factor of 4 because it's a quarter of R. So the new resistance is going to be 1 over 4 of the original resistance. So I can simply say resistance, because it's a quarter, it decreases. If it was 4 times R, it would be increasing by a factor of 4. So I'll say resistance decreases by a factor of 4. The resistance decreases by a factor of 4. I can say the new resistance R new is equal to a quarter of the original resistance. Then a section of the lightning rod of length 0.12 meters is removed for testing a tensile stress. So this is stress of 1.9 times 10 power 6 pascals is applied as shown in the figure. So the original length is 0.12 meters. The section of the rod obeys Hooke's law. So that means force is directly proportional to extension, and therefore stress is also directly proportional to strain. The Young modulus of copper is 1.3 times 10 to the power of 11 pascals. Actually, the extension of the section. Okay, so we want to find the extension. We know that Young modulus, my students normally use E for Young modulus, is equal to stress divided by the strain. Of course, the stress could be sigma divided by the strain. Also remember, strain is extension over original length. So it means the Young modulus is going to be the stress upwards, L naught goes up, so it is times the original length over the extension. That is simple mathematics, which means the extension is going to be the stress times original length over the Young modulus. So I'll substitute. Because they gave us the stress, I didn't use force over area. So the stress is 1.9 times 10 to the power of 6. The original length is given as 0.12, yes, 0.12, divided by the Young modulus, which has been given as 1.3 times 10 to the power of 11 pascals. So I'll just press my calculator. 1.9 exponent 6 times 0.12 divided by 1.3 exponent 11. So this is giving me 1.75 times 10 to the power of minus 6. So I'll just write here 1.75, or you can write 1.8 times 10 to the power of minus 6 meters. A pinball machine uses a spring to launch a small metal ball of mass 4.5 times 10 to the power of minus 2 kilograms up a ramp. The spring is compressed by 8 times 10 to the power of minus 2 meters and held in equilibrium as shown. So it has been compressed through this. So it means when it is released, it will lose the elastic potential energy as it gains kinetic energy and also gains gravitational potential energy through this height here, which I'm calling h. Of course, this angle is still 15 degrees if I draw a horizontal line here. Okay. The ramp is at an angle 15 to the horizontal. The spring obeys Hooke's law and has a spring constant of 29 newtons per meter. Calculate the elastic potential energy in the compressed spring. Okay, so we know that elastic potential energy is going to be equal to a half k x squared, or you can use f half fx, but f is equal to kx. So I'll just substitute here. This is going to be a half times k. K has been given as 29 times x. Of course, the compression is 8 times 10 to the power of minus 2, and that is squared. So this is going to be 0.5 times 29 times 8 exponent minus 2, but this should be squared. So this is giving me 0.0928, or I'll write 9.28 times 10 to the power of minus 2 joules, not meters. Alternatively, I will round off to two significant figures for simplicity, so I'll write 9.3 times 10 to the power of minus 2 joules. Then the spring is released and expands quickly back to its original length. So that means it loses elastic potential energy. Calculate the increase in gravitational potential energy of the ball when the spring returns to its original length. Let's first find the height h. So this distance is 8 times 10 to the power of negative 2. The height h is in the opposite. So we have sine, opposite hypotenuse, that is sine. So sine of 15 is equal to the opposite, which is the height h, or the change in the height h, over the hypotenuse, which is 8 times 10 to the power of minus 2. That means the change in height is 8 times 10 to the power of minus 2 sine of 15. That is the vertical height, or the change in the increase in the height. So the question is calculate the increase in gravitational potential energy. So the increase in gravitational potential energy is going to be mg times the change in the height h. So I'll just now substitute the mass. What is the mass of the ball? The ball is 4.5 times 10 to the power of negative 2 kilograms. 4.5 times 10 to the power of minus 2 kilograms, that is the mass, times G, 9.81 times H. We have already seen that H is 8 times 10 to the power of minus 2 sine of 15. So this is H. So I'll just press my calculator. So from my calculator, I have 4.5 exponent minus 2 times 9.81 times 8 exponent negative 2 sine of 15. So it is giving me 9.14 times 10 to the power of minus 3 joules. Because I wrote one significant figure here, I'll also take one here for simplicity. So because I wrote two significant figures here, I'll also take two significant figures here for simplicity. You can still take two significant figures. So I'll write here 9.1 times 10 to the power of minus 3 joules. Then the ball leaves the spring when the spring reaches its original length. Assume that all the elastic potential energy of the spring is transformed to the ball. So where does this go? The elastic potential energy gives the ball a vertical height. That means the ball gains gravitational potential energy. And also it gives the ball kinetic energy. So for it to move upwards. So I'll simply say that the loss in elastic potential energy is equal to the gain in kinetic energy plus the increase. No, I will not say gain because the kinetic energy might not be increasing as it goes up. I will say change in kinetic energy is equal to the change in kinetic energy plus the increase in gravitational potential energy. So the loss in elastic potential energy, we have already seen that it will lose the 9.3 times 10 to the power of minus 2. Then the change in kinetic energy will be a half m. Let's say velocity changes from a certain velocity with which it is projected to 0 when it reaches the maximum height. So I'll just put here v squared. Or it will be v squared minus 0 squared at the highest point. That is the change in kinetic energy. Then plus the increase in gravitational potential energy, which we have got as 9.1 times 10 to the power of minus 3. So I'll simply say that a half times the mass of the ball, which was 4.5 times 10 to the power of minus 2, v squared is going to be equal to 9.3 times 10 to the power of minus 2 minus 9.1 times 10 to the power of minus 3. So I'm going to make a v the subject. So v will be the square root of, so this will be 9.3 times 10 to the power of minus 2 minus 9.1 times 10 to the power of minus 3, but this is times 2, divided by, I'm making v the subject, 4.5 times 10 to the power of minus 2. So I have to multiply with it by that 2 in the denominator over half. So I have 9.3 exponent minus 2 minus 9.1 exponent minus 3 times 2 divided by 4.5 exponent minus 2. Then I find the square root of the answer, and I'm getting 1.93. So this is 1.93 meters per second, or approximate, I can just write 1.9 to two significant figures. The ball comes to rest, which means final velocity becomes 0 on a horizontal trapdoor of negligible mass at a distance d from its pivot. A force F acts vertically downwards at a distance of 2 centimeters from the pivot as shown in the figure. The trapdoor is in equilibrium, which means the resultant force is 0. The sum of clockwise moments equal the sum of anticlockwise moments. Calculate D. So F is causing an anticlockwise moment. Then the weight of the ball will be causing a clockwise moment. And remember, the weight of the ball was 4.5 times 10 to the power of minus 2 newtons. So we want to calculate D. So by the principle of conservation of moments, the sum of clockwise moments should be equal to the sum of anti-clockwise moments about the same point. So the sum of clockwise moments should be equal to the sum of anti-clockwise moments, but let me start with the anti-clockwise. So anti-clockwise, I have F, which is 1.7, then times the perpendicular distance. Because we want the answer in meters, I will change 2 centimeters to meters. So this will be times perpendicular distance, which is 2 times 10 to the power of minus 2, should be equal to the sum of the clockwise moments, which will be the weight, which is 4.5 times 10 to the power of minus 2 times the perpendicular distance, which is D. So what is D? D will be 1.7 times 2 times 10 to the power of minus 2 divided by 4.5 times 10 to the power of minus 2. So I'll just press my calculator. I think minus 2 has cancelled, so I'll say 1.7 times 2 divided by 4.5 because power negative 2 has cancelled out. So this is giving me 0.7 point. Oh, this was mass. What is 4.5? This is mass, not weight. Sorry about that. This was kilograms, so this must be times 9.81 to find that force there. So there is something missing here. I'll have to change here because this was not a force, it was mass. So this is, the force is 4.5 times 10 to the power of minus 2 times g, which is 9.81. That is the force, then times the distance. So here I have to say times 9.81. Yeah, that's why the answer was very weird. It was not really making good sense. So I will divide this by 9.81. So this is 0.077, I think. Yeah, which is 7.7 times 10 to the power of negative 2. So 7.7 times 10 to the power of minus 2 in meters. Then our force F is decreased from 1.7 newtons. State the direction of the resultant moment. So if the force is decreased, it means, remember initially it was equilibrium and the distances have not changed. So if F decreases, it means the anti-clockwise moments become less than the clockwise moments. So that means the resultant moment must be clockwise because the anti-clockwise is less than the clockwise, so the resultant must be clockwise. The resultant should be clockwise. Because if we reduce F, it means the anti-clockwise moment has been reduced. It's no longer equal to the clockwise moment. Because the clockwise moment has not changed, it means it is greater than the anti-clockwise moment. So it means this moment here has reduced. The moment on the right-hand side has not reduced. So it means the beam will move clockwise. So the answer here is automatically clockwise. State Kirchhoff's second law. Of course, Kirchhoff's second law is a consequence of conservation of energy, and I think it is a very easy law to state. The sum of EMFs around a closed loop is equal to the sum of PDs around the same loop. The sum of EMFs around a closed loop. It should be a closed loop or a complete circuit equals to the sum of PDs or potential drops around. It is allowed to write PDs, please, around the same loop. So that is Kirchhoff's second law. Remember, the first law is algebraic sum of currents into a junction on a junction is 0. The battery of EMF 9 volts and negligible internal resistance is connected in series with a variable resistor X and a thermistor Y as shown in the figure. So we see X and Y are in series. The figure shows the relationship between temperature and resistance for a thermistor. The current in the circuit is 1.1 times 10 to the power of minus 2. The PD across Y is 4 volts. Calculate the resistance of X. So we want to find the resistance of X. Remember, the current is the same because they're in series. The PD across Y is 4 volts. Using potential dividers, if this is 4 volts, then it means the balance goes to X. So for X, it is going to be 9 minus 4, which is 5 volts. That is the PD across X. So I want to find the current, the resistance of X. So first of all, I will say the PD across X is equal to 9 minus 4, which is 5 volts. Then using Ohm's law, I know that resistance is going to be V over I. The V is 5 volts and the current is the same, 1.1 times 10 to the power of minus 2. So I'll just check with my calculator. 5 divided by 1.1 exponent minus 2. So this is 454.54 recurring. I'll just write approximately 455. This can be 455 ohms, or if you want two significant figures. Now for two significant figures, you must be very careful here. The digit after 5 is 4. So if you want to round off the answer to two significant figures, it will instead be 450, not 460, not at all. It is either 450 or 455. But for me, I'll write here 455 ohms. It cannot be 460 if you are good at rounding off. That is very obvious. The temperature of Y is changed to 190 degrees Celsius. The resistance of X remains unchanged, so it is remaining 455. Determine the new potential difference across Y. Let's first see the resistance of Y from the graph. 190 degrees Celsius. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that is 190. And the corresponding resistance is, I think this is 25 ohms. So from the graph, resistance of Y is 25. So I'll say from the graph, R for Y is going to be 25 ohms. So now remember they're in series. So I will say total resistance, R total, is going to be 25 plus 455, which I think this is 480. That is total resistance in series. Remember the PD, the EMF has remained the same. So the current must have changed because the resistance has changed. So I'll first find the total current in the circuit. I is equal to the EMF divided by total resistance, R total. So this is going to be the EMF has not changed, is still 9.0 volts divided by 480. So that is the current. So I want to find the PD across Y. So I have several options. I know the resistance of Y, I know the current, so I can use a formula. I can say the PD across Y is going to be the current, which is 9.0 over 480 times the resistance of Y, which is 25. So I can check this, 9 divided by 480, then times 25, which is 0.47. I'll just write 0.47 volts. So this is 0.47 volts. Alternatively, you could find the PD across X and then subtract it from 9. But this is a more direct route. V equals to I, this is current, times resistance. I've just used the V equals to I times R. The current is the same. This is going to be resistance for Y. That will give us PD across Y. So that is 0.47 ohms. The resistance of X is increased. The temperature of Y remains constant. Rx is increased. Temperature of Y remains constant, which means the resistance of Y has remained 25 ohms. So the resistance of Y has not changed. By reference to the current in the circuit, state and explain the effect of this change, if any, on the PD across Y. So I'll do the mathematics here for us to understand. So number one, the PD, first of all, total resistance is equal to the resistance of X plus the resistance of Y. The resistance of Y has not changed, resistance of X has increased. So when resistance of X increases, it means total resistance has increased. And remember, the current is equal to the EMF over total resistance. That is the current in the circuit. So if the total resistance has increased, so it means total current has decreased. So it means the current in the battery has decreased. If the current in the battery has decreased, then what happens to the PD? I mean, of course, the same current goes through Y. So the current in the battery has actually decreased. If I use V across Y equals the current times the resistance of Y, because the resistance of Y has not changed, but the current has gone down, then Vy has also gone down. So that is obvious. So I'll simply say increasing. Because there are 3 marks, I must be very careful when I'm writing this. So I'll say increasing resistance of X causes the total resistance to increase. So the total resistance is going to increase. And if the total resistance increases, it means the total circuit current decreases. So the total circuit current decreases. Total current circuit decreases. And if the total current circuit decreases, remember I've just showed you that PD across Y is equal to the current times resistance of Y. Hence, the PD across Y decreases. As simple as that. Question 6 is waves. Light of a single frequency is incident normally on a diffraction grating. An interference pattern of bright and dark fringes forms on the semicircular screen. The light has wavelength 20 nanometers. Nano is 10 to the power of minus 9. The separation of the lines in the grating is this. So this is going to be D. This is wavelength. Determine the total number of bright fringes formed on the screen. We want the total. So if this is a diffraction grating, first of all, it forms the zero order. This is n equals to 0. Then it will form n maximum on one side and n maximum on the other side. So we have the total number of orders the other side, total number of orders this side, plus the one at the center. So let's first of all find out n. We know that n lambda is equal to d sine theta for a diffraction grating. And for n maximum, theta is going to be 90 degrees, which means sine theta is going to be equal to 1. So it means n is going to be d over wavelength because sine theta is equal to 1. So d is 3.8 times 10 to the power of minus 6 divided by 520 times 10 to the power of minus 9. So this will give us 3.8 exponent minus 6 divided by 520 exponent minus 9. So this is giving us 7.3. This is 7.3, but n must be a whole number, so we just round off this to 7. So we have 7. The maximum this side is n equals to 7 below the center. The maximum the other side is n equals to 7. So we have 7 plus 1 at the center plus another 7 total. So it means the total number is going to be 7 plus 1 plus 7, which gives us 15. Total number of orders is going to be 15. So the answer here is going to be 15. If you say 14, you will lose 1 mark for this because they want the total number of bright fringes. The light is replaced with the red light. Of course, this is 520. Red has a wavelength of about 700 nanometers. So it means red has a longer wavelength compared to the one which is given. So it means it has a smaller frequency. State whether the frequency of red light is greater than, less than, or the same as the frequency of the original light. Red has a longer wavelength, therefore it has a smaller frequency. So that means it is less than, frequency is less than the original light. I'm saying the wavelength of red is 700 nanometers, so it is longer than 550, which was given. And remember, wavelength from V equals to lambda times F. The wavelength is inversely proportional to the frequency. If red has a longer wavelength, then it has a smaller frequency, so it is less than the original light. State and explain the effect of this change on the number of bright fringes formed on the screen. A calculation is not required. So remember, we have said that n is equal to d sine theta over lambda, where sine theta is 1, so n is equal to d over lambda. The wavelength has been increased, so it means the number of orders decreases because they are inversely proportional. So I will simply say red light has a longer wavelength. Red light has a longer wavelength, so the number of bright fringes formed decreases, or we would say will be fewer, or will be fewer. Okay, so the number of bright fringes decreases, or they will be fewer because red light has a longer wavelength and n is inversely proportional to the wavelength. And lastly, particle physics. A particle Q and a particle R are each composed of one quark and one antiquark. a quark, and an antiquark. Those are automatically baryons. Particles which are made up of quarks are hadrons, but specifically hadrons which are made up of a quark and an antiquark are called mesons. So state the name of the class or group of particles that includes Q and R. So these are either you call them mesons to be specific, or you just call them generally hadrons. Remember, hadrons are classes of particles which are made up of quarks, but hadrons are of two types. We have the mesons and we have the baryons. The mesons, this is a quark plus an antiquark. Then the baryons, these are basically three quarks, not three antiquarks. So specifically, either you call them mesons because it's a quark and an antiquark, or just call them hadrons. So it is mesons or hadrons. Q has a charge of minus 1e, where E is the elementary charge. R has a charge of 0. Complete the table to show a possible second quark in each of Q and R. So they said each of them has one quark and another quark, which has one quark and one antiquark. So let's start with the first one, with the Q. Q has its total charge as minus 1e. Remember, the charge of a strange quark is negative 1 over 3e. That is the charge of a strange quark. What is the second quark? So total charge should be minus 1e. So I have that negative 1 over 3e plus the unknown charge of the second quark should give us negative 1e. What is x? So x is going to be negative 1e plus 1 over 3e, which is giving me negative, I think this is negative 2 over 3e. So the charge of the second quark must be negative 2 over 3e. And which particles have this charge? We have the anti-up, we have the anti-charm, or we have the anti-top. Any of those. So I'll just choose one of them. I'll say anti-up. Ant-up. Or you can say, you don't need to say all of them. You can say ant-charm. Or you can say ant-top. Or instead of this, you can put letters, for example, ant-up. Or you can say ant-charm. Or you can say ant-top. You don't need to say all the three, just say one of them. So I'll say ant-up. Then for R, the charge of an ant-up we have already seen is negative 2 over 3e. So one particle has negative 2 over 3e plus x should give us 0. So x is equal to positive 2 over 3e. So which particles have positive 2 over 3e? Those are the up, or charm, or top. So here I can say up, or you can say charm, or you can say top. Now you don't need to say all these, you just choose one. Or you can say U or C or T, one of those. I think that marks the end of this paper. Like I told you, it was very easy and my students did this one. So I'm very certain they have really excelled. Until next time, bye-bye.